Okay, we are going to, in this video, we're going to calculate the pH of a weak acid solution when we know its concentration. And I call these H plus squared calculations for a reason which we'll see later why we call them that. And it's a good idea to do that, because as later on we'll see there's certain times when you can't use this technique. Okay, and it's important to know the limitations of it. Okay, but first of all, we've got this solution of ethanoic acid. When they tell us the Ka, you need to know the Ka, and they tell us the concentration of the ethanoic acid. Right, now what you can't do is say, right, Ha concentration is 0.015, so therefore the H plus concentration is the same. That's not true, because not all of the HA dissociates, only a small proportion of it dissociates. So you can't use that technique that we used with strong acids. So the way I would do it is this. I write down, right, instead of writing down ethanoic acid, I'm going to call it HA, and it's going to lose one of those protons. Okay, so HA dissociates into its conjugate base A minus and acid and the H plus ion, sorry. Right, now what I would write down the side here is I would write down start concentration. Start concentration. Now it's concentration I'm going to write down here, not moles. And I'm going to write down equilibrium concentration. Right, so let's look at the start concentration. The start is when you just put in the weak acid into the water and it hasn't, none of it has had a chance to split up into A minus and H plus. So let's call, what is the start concentration? They tell us it's 0.15 moles per decimeter cubed, so 0.15. The start concentration of A minus, well, we haven't got any because none of it's split up, so that's 0. Now the concentration of H plus, if it's neutral water, will actually be 1 times 10 to the minus 7, but we can ignore that because it's such a small number. We're going to get a lot more, so that's an okay approximation just to call that 0. The next thing to do then is say, right, well, let's imagine at equilibrium, the concentration of HA is dropped by X. So that means the equilibrium concentration of HA is 0.15 minus X. So what would be the concentration of A minus? And hopefully you can see that would be X. And the concentration of H plus would also be X. Okay. Now we know our expression for Ka. Ka is equal to concentration of A minus over times H plus over HA. So let's put the numbers into this equation. Okay, so we're going to get, we know Ka. I won't write that down just yet. I'll write down K. I'll write it down 1.74 times 10 to the minus 5. A minus concentration of that's X, and H plus is X, so I'm going to call that X squared, which is why I tend to call these H plus squared calculations. Okay, that's very important here, that the concentrations of these two things are equal, because when you make 1 mole of A minus, you make 1 mole of H plus, right? And that's going to go over 0.15 minus X. So you can see we've got this expression now, and the only thing we don't know is X. So we could solve it and we can find out X, and what is X is the H plus concentration, and we can work out pH. So you can probably see that is, if you expand that out, you're going to end up with a quadratic equation, which is a bit of a pain to solve. So there's an approximation which is perfectly valid, and it makes it, you can check, it makes no difference to the final answer you get. But we can say, because it's a weak acid, this value of X is tiny compared to 0.15. It's very, very small. So that means, we can say, because it is weak, .15 minus X is approximately equal to 0.15. So let's put that into the equation there. So then we end up with 1.74 times 10 to the minus 5 is equal to x squared over 0.15. And that means we're not going to have a quadratic equation, so I'm going to just multiply that out. So we get x squared is equal to 0.15 times which is 2.61 times 10 to the minus 6. And don't forget x is equal to h plus concentrations. That means h plus squared is equal to that. So we want to get h plus, just take the square root of that. Which is equal to 1.62 times 10 to the minus 3. And then we need to use our pH expression, don't we? pH is equal to minus log of the hydrogen ion concentration. So pH is equal to minus log of that number, which is equal to 2.79 to 2 decimal places. So that is our answer. Okay, so we've got the pH of the ethanoic acid solution of what we started off with there. Now, this you can see if you just look at this point, you get to a point here where, right, what have we got? Let's just put a box around this. Effectively, what have we got there? This 1.74 is the Ka, so we've got Ka is equal to that's H plus squared, isn't it? Yeah. And this bottom 1.15, well, that is the concentration of the HA. Okay, so you've got this little expression here. Ka is equal to, so you can work that out, but be really careful of using that expression because it is not always true. This expression is only true when the concentration of A minus is equal to H plus. So if you've got a weak acid and you add anything, it's okay when you've just got the weak acid and you've added it to water, but you've added anything else to it, like sodium hydroxide or acid or some conjugate base, then this is not true. So this is only true when it is a weak acid in water with nothing else added. And we do a load of calculations later on with buffers, we may have heard of, where you do add stuff. So that means you can't use this expression. So this expression is not always true at all. And so I think rather than memorize that expression, I see people go wrong a lot doing that, is think about logically, do this every time. And then you are thinking, you're not just doing it, putting numbers into an equation which you don't really understand, which is an equation which isn't true all the time. Okay. So that is the basic H plus squared method for calculating the pH of a weak acid.